All right, so it's kind of different here, hearing all these masters of diffraction talking about work from before I was born. And unlike many of you, sorry, I don't have Bob's phone number. I didn't ask him to solve my problem, so I had to learn a bit more diffraction myself. I'm also going to try to give more of a modern perspective, not what has been done in the past, but what we're looking to do with diffraction going forward. So hence the title, Extending Limits. I don't need to tell you all of this, right? The three things you try to get out of a powder diffraction pattern are peak intensities, peak positions, and peak shapes, and you all know the great things it can do with this. Shapes have been somewhat underrepresented, and we put some time coding to make life with shapes better. I'm also young and impatient, so I put in twice as many slides. The intent is to go fast. But if I don't, Bob, Brian, just give me a warning 3 minutes before I'm supposed to be done. All right, dark side of the moon of hole pattern fitting. So we came across this problem of cobalt metal. With a nanoscale synthesis, 2 polymorphs, both nanoscale, both anisotropic, probably in size. No good models that we tried could fit it. Normal rebuild failed, poly failed for good reason. Advanced shape methods, anisotropic size, stacking faults, all of those failed as well. So we started asking why it failed. We dug into the methods, and we invented a new method, which we call IPx, hole pattern fitting intensity position, but freely refined shapes to address. And once we did that, wait for it, then we could get very nice fits of the data, and we could do this with a structural model. Our intensities modeled, our positions are modeled, so we could do quantitative phase analysis in a way you couldn't if you were doing poly or something like that, that freely refined intensities. So this is the dark side of the moon analogy. If you think about hole pattern fitting, there are essentially 3 things you might think about modeling or freely refining. Intensities you could model or freely refine. Positions you can model, freely refine, that's P. Shapes you can model or freely refine, that's S. And X we use to denote freely refined. So if we look at existing modes of hole pattern fitting, Rietveld IPS, model intensity, model position, model shape. Poly is like Rietveld, but you freely refine the intensity, so that's XPS within this framework. And if you just fit a single peak, that's XXX, and in Topaz you can do XXS, common shape model, common size model for a bunch of peaks. So these are the ones that were well implemented. Chatting with Brian, maybe he has one more sneaking around. But what we did is we wanted to go after this IPX. Again, keep the intensity model, keep the position model, but freely refine shapes. And there's some variants of this that we've been figuring out how to do also. IIX, you could do a better job of refining the intensities if you freely vary the position and shape. XPX would give you really good lattice parameters, and if your instrument is flawed, IXS allows you to sort of freely refine the instrumental error, which is probably a good thing to do if you're working with really old data. All right, so we've been coding to access these, and it's really nice, right? For those of you who do a lot of Rietveld, you're often doing a poly. You have a structural model, and you want to ask how good it is, how much of the information is missing. You do a poly where you freely refine the intensities. And if the change is negligible, your model is as good as it can be. And if it's a large, then you should go back and look for what's wrong with your structure. Well, we can do the same thing with shape now. If we take our new IPX approach that my student Adam Correa and I put together, you can ask the same question about morphology and strain errors, which have been a lot less accessible, right? Most of the time, we don't know if our model for size broadening or strain broadening or faulting is correct. And this IPX allows us to see what the magnitude of the error is. And it's very nice in that it tells us there's a characteristic fingerprint for different types of broadening, size, strain, or faulting, and we can go after that as well. So in the past, when people have worked on fitting peak shapes, it's usually one of 2 camps. Either we're going to fit the peaks independently on the left, but you're susceptible to errors if your peaks overlap, if you don't have constraints with the structural model. You can get very wrong peaks fitting your data. And on the right side is hole pattern fitting, double void, things like that, which will tell you how good your fit is, but it's difficult to know if your chosen model is the correct model, or if there's something better out there, or where are the weaknesses of my model? Where can I do a better job? So the IPX, because we use an intensity model, position model, we're very strongly constrained. So we can do a very robust job extracting peak shapes. And we can do a lot with the peak shapes that we extract. So here's an example of bismuth telluride nanoparticles from our collaborators with the Cause Large group at UC San Diego. It's a well-known structure, but the peak intensities are way off. If you look at the difference pattern below, we can see some very large differences, a factor of 2 in the maximum intensity of peaks. And when we run the IPX, where we freely refine the peak shapes, we can deal with these problems. So this is good if you don't care about what your shape is and just want to do a good job with the intensities. You want your structure model to be correct. It allows you to skip the step of modeling the shape of the material or the anisotropic strain of the material, no matter how fun it is for you to see them. But you don't have to do it if you don't want to. But we can still take these peaks and learn nice things from them. And what we've been trying to do is can we get the full three-dimensional morphology of nanoparticles out of powder diffraction data, even for very large things. So here's the bismuth telluride. We've automated the process of Williamson-Hall. You don't see a lot of Williamson-Hall in the literature. It's a pain to do. You have to go through peaks individually most of the time. But my group writes Python code. And instead of just a few peaks, we have 50 or 100 peaks. We actually had hundreds of peaks, but we threw out all the ones where the ESDs were large. So we can get the peak breadths of 50 peaks here easily. We see that our data is bounded. We've colored each point by its angle to the C-axis, the angle to the 001. We see all the broadest peaks are in the C-axis direction. All the narrowest peaks are 90 degrees away from the C-axis, so it tells us an upper size limit in the AB plane is an average size of around average mean column length of about 500 nanometers. And in the C-axis, we're looking at 40 nanometer mean column length, that's broadening the sample. And slightly different strains on the two, so we can start getting at the anisotropic strain, even when we have strong anisotropic size broadening as well. So it's all automated. It's just a push button, run the refinement, hit a button, and all this pops up, even the plots. All right, so here's a bismuth telluride sample. We got SEM data, confirms they're very platelet, as suggested by the Williamson-Hall, about a 10-to-1 aspect ratio. We've taken the size, the mean column lengths plotted versus angle of the C-axis. We can see a clear trend. Given this shape, we built up a rhombohedral model, and we did some coding for this to analytically calculate mean column lengths from the particle shape. So we can calculate exactly what they are for every reflection in this model. Non-trivial, but we worked it out. And very fast to run. I'll compare it to some other things in the next slide. But now our simulations can be directly compared to experiment. From our shape model, we get 760 nanometers between vertices. That's more or less what we see in the SEM data, but we didn't include instrumental broadening, which is why we've been talking with the NIST folks here who care about all the little details. So we're working on getting a good instrumental model for 11BM, and I think we can get reliable shapes up to, on the order of a micron. If you can do this for 500 nanometer distances, then traditional nanoparticles are not so bad. So this is prior work of my former student, Joanne Liu, during his postdoc at Oak Ridge. The shape models were done in a tour de force where they did atom by atom model building. Debye-Schrödinger equation goes as the size roughly to the 6th power. Not something you want to do for something big, and 30 nanometers was pushing the limits of what they could do. But the pictures are their shapes. The symbols are our data, and we can see without any further analysis, just the transformation of the data, we can see the platelets on the left, 10 nanometers one way up to 30 and the other, exactly what they found out in their very detailed model. Truncated octahedra on the right, 14 down to 10. When we take their actual shapes and put it in, we can see the peak-to-peak agreement. So it really looks like we have the sensitivity to get a full three-dimensional morphology, which is, of course, great for things like catalysis, right? The different facets can have activities differ by an order of magnitude. You really like to know what facets you have. And instead of counting them one by one, we can get a really nice bulk average from powder diffraction data. So filling a missing gap. And furthermore, good luck doing TM at high pressure, at high temperature, right? All these are easy for powder diffraction to do. So we have a very robust, very fast way of getting at particle morphologies from powder diffraction under operating conditions. All right, next story, heterogeneity in battery materials. So lithium iron phosphate was a hot battery material 10 years ago. It's still an important industrial material. And this material has one-dimensional fast diffusion channels. And there was some work by Sater, theory work, that suggests that 1% defects, 0.1%, 0.01% can very strongly affect the rate at which lithiums conduct and the performance of the material. So we grew single crystals again about 10 years ago and used single crystal X-ray and single crystal neutron diffraction on a time-of-flight instrument to study the defects, because single crystals are very good if you want quantitative intensities. Although our goal was to probe defects where iron was sitting on the lithium side and blocking the channels, single crystal refinements found bigger issues. Let's see. Here is a R value with no defects, 4.73. Put in antisites, it drops by about 0.2%. And then refine your oxygen occupancies, it drops by 0.3%. Refining the oxygen occupancies has a bigger effect on the model than the antisites of the iron metal or the lithium metal. And we studied 10 different crystals, and this was the case for all 10 of them, where we got about 3% excess oxygen on the oxygen sites in our refinements, which is completely aphysical, no way to put it in, no way to get a chlorine on the oxygen site. So this is telling us we have a more fundamental problem, which did not occur in the neutron data. So by comparing X-ray to neutron, we're able to see that this is a form factor problem. A nice chat with Phil Coppin said, throughout the high despacing data, where the valence electrons are contributing, and just look at the core electrons, this problem should go away, and sure enough, it did. So we confirmed that the valence electron distribution differs from the model used, the spherical model used in form factor calculations, which we attributed to the phosphate bonding, the very strong covalent bonding in phosphates. But it turns out it's not just a phosphate problem. We'll come back to that later. This was a mem map, looked just the same as charge density, but generated much more easily. So displacement parameters are a good check of the quality of a refinement. Here we look between X-ray and neutron, and we were shocked to see the lithium displacement parameters were agreeing to better than 1%. We're generally in the order of a few percent difference between X-ray and neutron. Here we're very happy to have GSAS, the ability to do time of flight absorption correction on single crystal data. Many flaws in shell X. We also had to work with extinction here. It was very strong for these crystals. If you're looking for a powder sample to do extinction, these had very strong extinction when we ground up single crystals. But we had a lot of faith that we're getting correct displacement parameters. When we all do structure refinements, if we want to test how robust the refinement is, we'll refine a site occupancy. And it never stays at 100%, right? It goes to 103%, 98%, 96%, 1 to 10%, depending on the material, your refinement, and the stability. But when we fix the displacement parameters to the single crystal values, which we believe, our occupancies were agreeing within 0.1%. That started being the magnitude of our error. So this told us that if you have the right displacement parameters, you can get much better site occupancies than you could otherwise freely refining these. And we've done lots of testing, and it's all the details in the paper, but any one powder refinement gave very unreliable displacement parameters. We refined them all together. In powders, we could do a much better job. But this told us that there are ways to getting much better site occupancies that have been done in the past. So we applied this to battery materials, took a dozen materials, the best data in this country, 11 BM for synchrotron. We've got Nomad data for our 200 milligram samples, and we can compare them together, and there were a lot of agreement between the two. We're looking primarily at paired andesite defects where nickel 2+ is a little bit large and it can swap with a lithium. That's the main defect. So what we found is that on the left were our standard refilled refinements. We found 2 to 5% defects. This generally sounds good, but the variation was more like 0.3% on average, 0.9% at max. It was not good enough for structural properties. But when we fixed up our ADPs by global refinements across all materials, when we fixed up form factor problems, which I'll tell you about in the next slide, we had agreement between independent X-ray and neutron refinements at the 0.1% level, and this may be limited by the knowledge of the composition of the samples. This is sort of a upper limit on what the sensitivity is. And 11 BM doesn't even have that good counts, right? They're better beamlines for getting very accurate measures of intensity. So we're already beating ICP by a factor of 10, and we could do about another factor of 10 with the addition of phase specificity, which chemical methods do not have. We know exactly which phase defects are changing in. So we developed these methods, F-star diagrams or diffraction phase diagrams. Instead of plotting occupancies or composition on a triangle diagram, we plot the scattering power at each site. Fantastic construction. I can go into the details another time. But essentially, it encodes all possible diffraction patterns you can get by varying site occupancies. Two-dimensional, so the global minimum, you find any two non-collinear defects, you find the global minimum. And in a dozen samples, we found the global minimum in the neutron data was this one defect of paired andesite defect. So we know this is the dominant defect. It's not an accident that they're all, 99% of the improvement in the refinement comes from paired andesite. So we had a lot of confidence in this defect. But the X-ray data did not tell us it was almost all paired andesite defects. And that allowed us to see some limitations in the X-ray treatment. If we look at all the X-ray samples, ignore these two, which had two defects, not just one, but all of these, if we plot them on the F-star diagram, we can see that not only do they all have a similar magnitude of defect, but it points in about the same direction. Each defect has its fingerprint. This points to the oxygen corner. We need to make the oxygen about 2 or 3% more occupied to fit the problem. That's not happening in the material. This is a problem with the X-ray form factor, just like we saw single crystal data, thanks for the nice refinements, Bob, in lithium iron phosphate. But this is a traditional oxide without the phosphates, without the oxoanion groups, and we're having exactly the same problem. So this problem is probably there in every other oxide compound that people have studied by X-rays. Form factor error on the order of 2 or 3% is no longer small relative to refinement uncertainty since we cleaned up other problems. So we now need to worry about it. Some work needs to be done to find better form factors. And I find it spectacular we could resolve the form factor problem in oxygen from a 5-element mixture on a 3-site compound. This is not what we expected starting, but this is what the data said, and it's consistent with various observations in various places. Once we have accurate occupancies, we can use Boltzmann to turn them into an energy for defect formation. Everyone said the andesite defects form because lithium and nickel 2+ are the same size. To give a constant defect to energy is not constant as we see from our data. It says it's the overall expansion of the lattice and the size of the octahedra that matters, not the size of the atoms themselves. So some coherency strain. yeah, DFT was way off, so experiment's the only way to get good numbers. And once we have the energies, we can predict how the defect concentration versus temperature. So certain compositions have always seemed to have the same defect concentration, but now post-annealing can tune them. So we started doing some of that work. And this is one of my favorite tables. Funny things happen. There are multiple defects involved, not just one, and two of them are active up front in early times. But what we can see is that the change in defects relative to a 1 day of annealing, X-ray 0.0021 is the defect concentration, neutron 0.0023. After 4 days, 0.0034, 0.0033. We're agreeing to the fourth decimal, 1 in the fourth decimal for our site occupancies, which is spectacular. We haven't seen anything like this. If you do, please let us know. Mean square difference, mean difference about 3 parts in 10,000, but that's the sum of the X-ray and the neutron. So if you just did one, your sensitivity is probably better. So here we're actually getting at the kinetics of the loss of 1% lithium over 2 weeks of annealing. Red was the neutron data, black is the X-ray, so they're a very good agreement. Again, independent refinements. With the same B value in both of them, that's important. And if we plot the defect concentration versus square root of time, it's very linear, which says random walk diffusional processes, and that's consistent with how lithium might come out of the material. And the mechanism and the kinetics are confirmed through TGA studies. More interesting things there, which I won't speak about in the interest of time, but a lot of more information than we thought in powder diffraction patterns. All right, so Bob, happy birthday and thank you. We haven't gotten to work together much in the past, but I will say that a substantial amount of my crystallographic education came from the GCES manual. We really appreciate all the details in there. I did my PhD in a group doing physics stuff, so we just did phase ID and had no real appreciation for how much more there was in diffraction data, but I've been slowly learning over time. And we even use GCES to validate other software tools that we use. Crystallography, I find, is somewhat mystical, right? Things seem incomprehensible until you understand them, then they're easy. Crystallography is not easy to learn. We appreciate the efforts of Bob teaching, including at the modern methods of Rietveld refinement structural analysis. I did, again, modern. 30 years later, you can make fun of me in 30 years. That's totally fine. But I thought it was great. I mean, the first few times I tried to understand Rietveld, it was a mess. I couldn't figure it out. When I started learning single crystal diffraction, spent a few years as a small molecule crystallographer, then I learned how things should be, and then I could understand why the powder wasn't the way it should be. And then all started to make sense. And really appreciate that GCES has both the powder tools and single crystal tools together. That's smart for somebody who understands their crystallography. So thank you for teaching at the school. And another really important point, I mean, everybody talks about the next new synchrotron, the next new neutron source. But in our experience, we found that software is every bit as important in hardware as advancing crystallographic frontiers. New facilities cost billions of dollars, new software, millions of dollars or less. And it's sort of a similar rate of advance in what we can do. So it's really fantastic, Bob. You put all this time and effort in developing software bits that are responsive to user requests. And I would say your investments are clearly shown to be foundational and exponential. My generation and the generations after, it's really allowed us to elevate what we can do with crystallography, with powders, with single crystal. Here's the school. Thank you, Bob, for teaching. A few instructors in front, and this was 30 students at the APS in 2018, learning fundamentals of crystallography, including powder diffraction analysis. Teaching is really important. The students at the school are very appreciative. It's not easy to learn crystallography, so all the time and effort really counts. Looking forward, drinking from the fire hose, I call this. A lot of our ongoing work has been with 2D area detectors. We get a pattern once a second, once every 2 seconds, we'd go 10 times faster if the readout was faster. So we've been trying to deal with all this data. All my students learn Python these days. That's the only way we can deal with this much data. Here are some essentially live refinements of in situ ion exchange kinetics. Here's the salt shrinking, the ceramic shrinking, salt increasing, live updates of the patterns. Here's the rate constant coming out live at the beamline, so we can tell how our experiments are going. If we've reacted long enough, we can make decisions at the beam time. We tried with GCES, but it started hanging up after 1,000 patterns got loaded, and maybe it's better now. This is.
That's where you want a script.
It was a script, but it was yeah. All right, it was in GUI. Yeah, okay, not through the script. Here are battery materials that we've taken a battery, this film 150 microns thick. Imagine slicing it up like a postage stamp. With a 10 micron high beam, we can get the response of each different layer. We can look at the state of charge difference between the bottom layers in dark, the highest layers in red. And we can look at how this depends on charge rate, and we can fit this with modeling. And any model that fits data like this has to be a pretty good model to be a multi-dimensional fits. The stuff on the right is us using a powder diffractometer to do single crystal diffraction work. Here's a 3 centimeter boule from a floating zone crystal, powder at the bottom, the single crystals on the top. And what was really curious here is that this is sort of a composite image for everything on the line. You can see it moving from left to right. On the left side of the crystal, the peaks are very spread out, indicating a lot of mosaic imperfection. On the right side, they're very spread out, but in the middle, they tighten up, which I think is telling us something about the influence of the curvature of the solid-liquid interface on the single crystal growth. This is something that's not been controlled in the past, but we're trying to get funding to do in situ studies of crystal growth, where we could actually probe the interface live. The fraction pattern of a liquid and a solid are pretty different, no matter what the liquid and the solid are. So yeah, we're doing a lot of work to try to do analysis fast enough to guide data collection, live temperature, live structure, live kinetics. This is the future that we've been pursuing. So with that, I'll conclude. Battery crystals, single crystals, that's the work of Yuri Jansen, a former postdoc at Farmingdale State, Liang Yin, Yue Zheng, a PhD and master students who did the very careful defect quantification. All the floating zone work is Yisu Wang. Live ion exchange, those are scripts written by Monty Cosby. Now it's LAC, looking for a faculty position. Adam is done and is about to defend the work on nanoscale morphology and wrote all the code for Williamson Hall and this IPx peak extraction. Big thanks to all the user facilities and the people who support them, as well as the regular funding for the research. And thank you, and I don't have to answer any questions. But again,